Last time we began to derive the distribution functions for quantum statistics. We did the simplest one, the one for photon statistics. Photons are a simple case, a special case of Bose-Einstein statistics. What I'd like to do is start today with Fermi-Dirac statistics and derive that distribution. So we're going to examine a case, in this case, where the total number of particles is fixed. It's capital N. And so if I sum all of the particles and all of the states, of course, I'm going to get capital N. That is a constraint. I'm going to use a notation. I'm going to use the notation sigma with a parenthesis, S in parentheses. I've got that means sum over all of the states, N1, N2, etc., except for state S. Okay? So this is a sum over all the states except S. You'll see why this becomes important to us. So I can write the term Z sub S of N as the sum over all states except S, e to the minus beta, N1, N2, E2, etc. If I know that the sum over all states N sub R is equal to N. Now, since we're using Fermi-Dirac statistics, we know that N sub S, the number of particles in state N sub S, is either 0 or 1. 1's the upper limit. So what I'm going to do is perform the sum explicitly so that I get everybody involved. So it's going to be N sub S is equal to 0 for the case where I don't have anybody in state S, plus e to the minus beta E sub S, that's when I have somebody in state E sub S, and then the rest, times Z sub S of N, N minus 1. So this takes care of the whole rest of the particles in the gas. And I'm going to divide that by Z sub S of N plus e to the minus beta E sub S times Z sub S of N minus 1. So this is, denominator is the total partition function, sum over all the states, and then the numerator is N sub S times each, as we would call the Boltzmann function. I'm going to rewrite this, though, make it a little bit simpler. Z sub S of N divided by Z sub S of N minus 1, e to the minus beta E sub S plus 1. Now that may not look that easy, but we'll be able to do a few things with this. That being the case, what we want to do is see if we can simplify this relationship right here. Ask ourselves, can we do this? And maybe we can say, suppose that the difference between, let's say, N and N minus 1 is very, very small compared to the size of N. So maybe N is a very, very large number, and then, so N minus N minus 1 would be a very small number. The way we can write this is just to say, well, delta N is going to be much, much, much less than N. If I do that, then I can say the following. Then I can say the log of Z sub S of N minus delta N is equal to the log of Z sub S of N minus d log ZS. And so in other words, I'm expanding this in series, delta N. And I can write this as log ZS of N minus, we'll call it some alpha sub S delta N. So alpha represents d log Z dN, okay? That should look familiar to you, but we'll get to that in a second. So what this is saying is Z sub S times N minus delta N would be equal to z sub s of n times e to the minus alpha sub s times delta n. And of course, alpha is just d log z dn. Now, here's the trick. Since z sub s of n is the sum over many, 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 many states, the variation of its logarithm with a total number of particles is going to be insensitive as to which particular s we choose. So let's just get rid of the alpha sub s. It doesn't matter. It could be any state. Alpha is going to be the same. Alpha is going to be independent of s. That being the case, I'm going to write alpha as d log z dn, and if n is equal to, I should say if delta n is equal to 1, I can write this as n sub s is equal to 1 over e to the alpha plus beta e sub s plus 1. And this is the Fermi-Dirac distribution. Okay, the average number of particles in a particular state S. That's what we mean by a distribution function. Well, so we want to determine what the heck alpha is. So let's do that. We can do that by the normalization condition. If I sum over all states, 1 over e to the alpha plus beta sub e r plus 1, that sum has to equal n. Now, since the Helmholtz free energy can be written as minus kT log z, I can write alpha as minus 1 over kT df dn. So it's a derivative of the Helmholtz free energy with respect to the number of particles. By the way, we know this from before. We know that we've defined the chemical potential as df dn. And so what this is saying is alpha turns out to be minus mu over kT, or minus mu times beta. The chemical potential. That being the case, as n sub s approaches 0, I should say as e sub s approaches 0, n sub s approaches 0. But no matter how small e becomes, this denominator can never be less than 1. That's why that means that n sub s can never be greater than 1, which of course is completely in line with the Pauli exclusion principle. We expected this to happen. So we've got another one down. This gives us the distribution for the Fermi-Dirac statistics. Now let's go to the messiest one of all. Let's do the Bose-Einstein case. It's messy, but the good thing is we use the exact same logic that we used with Fermi-Dirac, except we've got more than 2 terms in the numerator, whereas in the Fermi-Dirac case you had 0 or 1. But again, we'll see that this will all work out in a similar manner. Again, we've got a constraint on the number of particles. I can write n sub s, I can write this out explicitly, and this is a little messier, plus e to the minus beta e1, z sub s of n minus 1, plus 2 e to the minus beta e sub 2, I'm sorry, e sub, yes, e to the minus z sub s of z minus 2, and all the way up, because now I have an unlimited number of particles that I can fit in one state, if I wish. All divided by z. Then plus e to the minus beta e sub s, z sub s of n minus 1, plus e to the minus beta e sub s, which is 2 beta e sub s, z sub s of n minus 2, plus and so on all the way up. But again, we can make the argument that we made previously. any change in n is going to be much, much, much smaller than n itself. That being the case, I can write my mean as z sub s of n times 0 plus e to the minus beta e sub s times e to the minus alpha plus 2e to the minus 2 beta e sub s e to the minus 2 alpha plus on and on and on, all divided by z sub s of n 1 plus e to the minus beta e sub s e to the minus alpha plus on and on and on. This is going to look like sum over s, n sub s, e to the minus n sub s, alpha plus beta e sub s, all divided by sum over s, e to the minus n sub s, alpha plus beta e sub s. Minus 1. And so I can write this then as n sub s for Bose-Einstein 1 over e to the beta e sub s minus mu minus 1. Notice the difference between the distribution function for Bose-Einstein and Fermi-Dirac. It's a minus sign, but it's an extremely important minus sign. You see we got a plus 1 down here, we have a minus 1 down here, and that has made all the difference. So, in the special case of photon statistics, going back to where we started, mu in the case of photons is 0. Therefore, if I remove this, of course, I regain the Planck distribution as I must. This is the case, the Bose-Einstein special case of photon statistics is when I have an unrestricted number of particles. In the case of photons, that's always going to be true. Okay, so you see how we've come up with these lovely distribution functions for quantum. What I want to do next is the following. We're going to go a little bit deeper into the weeds with the partition functions, because what we want to do is calculate systematically the partition function for each type of statistics, including Maxwell-Boltzmann, and find explicit expressions for z in terms of energy levels of a single particle. And we can use that kind of expression to help us calculate thermodynamic quantities such as entropy and others. So that's what we'll do as we move along. Let's start with the simplest case. We'll start with Maxwell-Boltzmann statistics. That being the case, notice my partition function is the good old Boltzmann expression we had before, sum over r, e to the minus beta, n sub 1, epsilon sub 1, n2, 2, all the way up. We evaluate the sum by summing over all r states of the gas, but taking into account that the particles are distinguishable in this case. So if I have n molecules, or n particles, then I'm going to have n factorial over little n1 factorial, n2 factorial, number of possible ways in which the particles can be put into a single particle state. So I would write z then as sum over all of those particles n factorial, and 1 factorial, and 2 factorial, and so on, e to the minus beta, n1, e1, n2, e2, and so on and so forth. So that being the case, again, using that constraint that the total number, n sub r sum over r, is equal to n, we're constrained by that, we can also write z in the following way. I can write it as the sum of n1 and 2, so I'm summing over all the particles, n factorial, and 1 factorial, and 2 factorial, all the way out, e to the minus beta e1, that's n1, e to the minus beta e2, times n2, e to the minus, et cetera, et cetera, et cetera. Which is to say I can write this as z is e to the minus beta e1 plus e to the minus beta e2, all to the nth power. Very simple. Log z then, another simple expression, n times the log of sum over r e to the minus beta e sub r. And so my mean number of particles in a given state S would just be minus 1 over beta d log z e sub s, which would be minus n over beta minus beta e to the minus beta e sub s divided by sum e to the minus beta e sub s. And simplifying, this becomes n e to the minus beta e sub s divided by sum over r e to the minus beta e sub s. This, of course, is regaining the Maxwell-Boltzmann distribution, which we did previously when we did classical statistics. We did this before. Nonetheless, it's nice to see that we get the same correct answer. Move on to the simplest quantum case. Let's look at photon statistics. In the case of photon statistics, I can write z as sum over r e to the minus beta n1 e1, n2 e2, n3 e3, all the way up. The summation is over all values of n sub r for each r, but there's no further restriction. There's no limit. There is no capital N limit. So in this case, I can write z as sum over n1, n2, n3, etc., e to the minus beta n1 e1 times e to the minus beta n2 e2, e to the minus beta n3 e3, and so on and so forth. I can break this into each individual sums, all of which can be summed at each geometrical series. And I can write z then, knowing the sum, 1 over e to the, 1 minus e to the minus beta e sub 1, 1 over 1 minus e to the minus beta e sub 2, 1 over 1 minus e to the minus beta e sub 3, and so on and so forth, all the way up. That means log z is going to be equal to sum over r times the log of 1 minus e to the minus beta e sub r. My mean number, my distribution, then my point distribution comes back, minus 1 over beta d log z de sub s, and of course that's going to be e to the minus beta e sub s divided by 1 minus e to the minus beta e sub s. Or, if you like, we can write this as n sub s is divided through by e to the minus beta e sub s. We get 1 over e to the beta e sub s minus 1. Once again, we regain, of course, the Planck distribution. Make it a little bit more interesting. If we want to look at the Bose-Einstein distribution, we want to evaluate that. We have z is equal to, here's for Bose-Einstein, sum over r e to the minus beta n1, e1, n2, e2, all the way up. But in this case, we have the constraint that n sub r sum must equal some capital N. So I have a limit. I don't have just an infinite sum. Makes my life miserable. So we've got to evaluate the distribution function differently because of this constraint. We're going to use a similar approximation to one that we used earlier. And we're going to make this argument. Because z depends on the total number of particles, n, if the total number were different, let's say it was n prime, and if that were the case, then z would be equal to z of n prime instead of n. We're going to argue that z of n prime is a very rapidly increasing function of n prime, since there are so many terms in the sum. But we're only interested in z of n prime when n prime is equal to n. That's the only time we're interested. So we get, in that case, z of n prime e to the minus alpha n prime, which is a function with a very sharp maximum. Why? This is a very quickly decreasing function. This is a very quickly increasing function. So we get a sharp maximum when we put the two together, as we've seen all along. So that being the case, let's fix the maximum. The max occurs at n prime equals n. We're just going to do that by fiat. And that's going to be fine as long as we choose alpha wisely. So what we need to do then is to say, let's write it this way. I'm going to write sum over n prime, z of n prime, e to the minus alpha n prime equals z of n, e to the minus alpha n times some delta star of n prime, where delta star n prime is the width of the maximum and is far smaller than n prime. Now I'm going to define, with this capital Z, a grand partition function. That's what we call it. I'm going to write it as z sum over n prime, z of n prime, e to the minus alpha n prime, such that log of capital Z is going to be equal to the log of, I'm going to say that, let's write it this way, log of Z plus alpha n is going to be equal to the log of Z of n. The log of delta star n prime is going to be negligible. So this is nice because I can evaluate this over all possible numbers without restriction. So it's just almost like doing the photon case again. I can write Z as sum n1 equals 0 to infinity, e to the minus alpha plus beta e1, sum n2 equals 0 to infinity, e to the minus alpha plus beta e2, on and on and on up the line. It's easy to sum them again. It's an infinite sum. it turns out that z is equal to 1 over 1 minus e to the minus alpha plus beta e1 times 1 over 1 minus e to the minus alpha plus beta e2 all the way up the line. That means,
1 minute, Dr. Bose.
okay, that log z is equal to minus sum over r log of 1 minus e to the minus alpha minus beta e sub r. That means log z, unscript z, is alpha n minus sum over r log 1 minus e to the minus alpha minus beta e sub r. Let's pick up with our evaluation of alpha next time.